Welcome back to week 14, the last week of the semester, except for a little bit of housekeeping and review right before finals week. We're dealing with 2 degree of freedom systems, and we're going to talk about coordinate coupling. So we have 2 coordinates, 2 degrees of freedom, and if we were going to write out the most complicated, well, not the most complicated, but a fairly complicated case. This is a general case right here. We would have, from those 2 equations of motion, this matrix. One term that we will look for, and will quite often happen, we'll have a diagonalized coordinates. These will generally be symmetric, by the way, just because of nature. But there is scenarios where we could make them non-symmetric. But what we mean by that is the diagonal, that might be its own thing and it's fine. But the off-diagonal terms, those will be equal. A lot of times there'll be some negative, but if this one's negative, that one will be a negative right there. If it doesn't have any diagonal terms, quite often that's the sign of what we describe as being non-coupled. Alternatively, if you do see things on the off-diagonal, and by off-diagonal we mean the things that are not in yellow right here, so that means that if we have the off-diagonal, then we're dynamically coupled. We'll either call it mass coupling or dynamical coupling. And the same thing true over onto onto the stiffness side. If we have off-diagonal terms or the non-diagonal terms, that means we have static and stiffness coupling. So here is an example, but I am way too lazy and too tired this semester to write all of this out. So I am just going to go and show you my results as I went through them. The book doesn't do this, doesn't work these out all the way, so I am going to supplement that by showing you what I did. All right, so we have this bar and 2 springs of differing stiffnesses, and the center of mass is not at the geometric center. It's at L1 and L2 right in here. So we could have, by the way, found out what JCM is. I went ahead and played around with it, but they're just going to leave JCM as a term. But I went ahead and found the mass moment of inertia for the entire thing, and then I transferred it over to the center of mass by taking moving these over. But doesn't matter. It's in a thought cloud, just something to think about. Okay, first I do the free body diagram. So here on the left-hand side, this is basically all they did in the book, was to show these out right here. We're going to use the motion of the in the x direction is going to be based on the center of mass, and then we're going to combine that with the angle that this thing moves through, right? So in this case, this has moved downwards x, and therefore this spring is pushing back on it, right? But it's the amount that it's pushing back is lessened by this displaced area, which is this displaced length, which is L1 times theta right here, because that's L1. Same thing true here, that this position x that this thing has moved is causing this force to be pushing up back and resisting it against there. But now, because of the angle, it's added to it right there, so you can see the 2 differences. On the right-hand side, we have both translation and this is the translation and the rotation. So in some of the forces treating downwards as possible, we have this plus this, or this, both of them negative sign, and then on the right-hand side, all we have is the translation. and that's at the center of mass. So I just rewrote it here as a nice handy equation of motion. We can also do the same thing with the angular right here. And in this case, we need a moment. And I decided to make clockwise positive, because generally speaking, the theta double dot, we're going to make that in the direction that the thing has moved, right? So it has changed direction, this direction, so I'm going to go and make that positive. And we're calling that the center of mass, right? So, and notably, by the way, we're also leaving out the mass times gravity in here, which we totally could have included if we wanted to, mg right in there, but we're neglecting him because there would have been static deflection in those springs, which would have worked out and made the thing nice and even to start in equilibrium before we did any kind of disturbance onto the thing. So this is going clockwise, which is we decided was positive. So it's clockwise, but remember that it needs to be a moment, so it's going to be times the L1 back in there. And same thing true to the L2 right here, but this is going counterclockwise, opposite from positive. So that ends up being in there. And then this is going clockwise as positive. So we can rearrange this and put these together. And if you look in the book, you'll see that this matches what they just gave you. They didn't work through this aspect of it. Okay, so the next thing I would notice right here, if you had the case that K2 times L2 was equal to K1 times L1, that would go away and that would go away, and that's mass is decoupled right now, and now the stiffness would be decoupled, and these would actually be decoupled equations. They wouldn't depend on each other, right? So that's an interesting type of result. So this shows the static coupling. Now we have this scenario, the what if scenario. What if there was a position, and there is a position somewhere along here, that if you were to place a force onto that position, this thing wouldn't rock back and forth, it would just translate. All right, so you have to find that position, and the distance between that position and the center of gravity would be, we're going to measure it as E. A lot of times they call it eccentricity. That's what I think of them right there. And so at that location, K1 times L3 is equal to K2 times L4, and we're going to need that in a second. So the book just jumps past this, and that always bothers me when books just pass over stuff, so I got to try to do it myself. Sometimes, I don't always do it myself. So here is this scenario where we have, okay, so here's the scenario we talked about. F at C, a force at C causes C to move, causes a displacement xc, but no theta. All right, so we draw our FBD and our IBD. Not a lot different. They did change the way that they were numbering this to kind of highlight that. Something I noted in trying to replicate what they did is they had to use kinematics. So we had, let's say that we know the acceleration at that point C, but when we go down to try to apply Newton's second law, we can only do it about the center of mass. So we need to find out what is the acceleration at the center of mass, saying that we know the acceleration of C. Well, what it's going to be C as a reference plus the angular acceleration, or you know, if we go to the three diagram method is usually what I would do, but this is pretty simple. So at this location with this G, we're going to give this plus whatever acceleration we have there. We can treat the thing as if it's still like horizontal. These are all small motions, and we don't have to worry about the normal. So this is the tangential acceleration that's being added to this known acceleration, or we think we would know it. So that's when we go down. That's the real difference that we have is we have this motion at C instead of at G, and we have the mass times acceleration at the center of gravity has this part because of kinematics right in there. So in the x direction, or excuse me, the translation, we would have all of this stuff, which is similar to what we just did in the previous example. And then we could just write them out along the way. But we did remember that the consequence of picking that spot, that magical spot, were that this was true right there. So what we've done is we've eliminated a little bit of the theta. Now if we come and we apply the summation of moments, and I'm doing the effective moments here, so it's not, we want to do it about the center of mass right there. So we're going to get two parts. We're going to have this part, and we're going to have this part right there. So we have, and by the way, what we've essentially done right there is we are going to kind of take the parallel axis theorem, just to kind of point that out. All right, so we have these parts to it right here. Okay, let me go back up to this and say this one is going clockwise, and it needs to be multiplied by L3 right there, right? L3. This one's going counterclockwise, and needs to be multiplied by L4. We also have from here, we have J theta double dot, and then we also have ME, mass times acceleration, right here, because we're taking it about this spot. I should have also mentioned that we're taking the moments about that spot E. So here is the rotational one, which didn't matter where we placed it. It just represents the whole thing. Then we also have a mass times acceleration times this, but it's also going to be times E right there. So that's where that E comes from. We bring these over and rearrange them, and we note that J plus ME squared is the parallel axis theorem. We still have a ME right here, an X double dot, and we also get this again, that little part right there, and then we have this last piece right there. So that's going to be from that and that and this and that. And so what we're left with is this equation, which is in the book. This is the one that the book provided. Let's see. Let's go back up to this. Did I miss something? I think I missed something. That's the general one. That's the one we're about to cover in a minute. Here's the one that we just found from our example. Oh, I know what's going on here. For whatever reason, this book, this PDF, is missing a couple of figures right here, right? So here was the dynamic coupling. That's the one we just got right there. So you see the dynamic coupling. So it just says that right there. I think it just slid down. Where we have the K1 times L3 is equal to K2 L4. That's the reason why that canceled out and that canceled out. And when we assembled them together, we got all of the same things. So you can see that they match, right? And I don't know why not everything is in there. They also, by the way, they left out a couple of figures in the PDF of the book. So here is the one we just did, and here's the other one. Now, one last one that we should take a look at is when we have. Now, let's take it about this spot instead, and so we're gonna have this spot. So let's take a look. I did that one out too. So this was the dynamic coupling, but it didn't have the mass difference coupling. If we instead start out with this orientation, they're about to tell us that we're going to get static and dynamic coupling right here. So here's an explanation for how that happens. So we're going to take everything, and now we're using as the reference x1, right? We're going to call him x1. So and the length, we're also going to call a length L1 that's from that. So we're going everything about here. So, and here's a little kinematics thing going on once again. I think that would be this guy right there. So here's a known, and here is a the known plus because of the theta double dot that we would have right there. So that's the acceleration. So that's the same thing right here in the sum of the forces in the x direction. I made positive downwards, that's a negative and I distributed them out. Now I bring them over. Now you're going to have two pieces to this, right? You're going to have the, oh no, it's just going to be mass times that acceleration. So that's why there's two pieces. There's the translational, here's like the rotational, but it's at the center of gravity. So that's the only one that really matters. So we can write them out here a nice long ways left to right. And then in a similar manner for the summation of the moments, I'm going to do it about what they called 1 right there. And so we have a stiffness times x1 right there, this guy. So he doesn't appear in here because we're taking the moments about that spot. And then over here we're taking both the spin and then also the effective moments, right? Because we're taking it about this spot right there. So we need to have both pieces. We're gonna see that we actually end up getting a parallel axis theorem term when we pull that out, and then have an ML1 and then plus the KLX and plus the L squared over all over L squared K2 times theta equals 0. So we can assemble these things together and get the same thing that the book got. All right, so the book had, here's one where we have both dynamically and statically coupled. Dynamically and statically coupled. One last one just to cover everything, and I have one more example after this. Let's see, coming back to here. There's the static coupling, right? So we already mentioned this. We demonstrated how we got this to this spot. There's the dynamic coupling. We demonstrated how we got to that spot. And there's the static and dynamic coupling. One last thing that they don't have a figure to go along with is the coupling by the damping matrix. Noticeably that these are not coupled in the mass and they're not coupled in the stiffness. Right, so it's like in this case only the damping is keeping these things together. Remember, that's related to the velocity. There are conditions where we have something called proportional damping, where those off diagonal terms are 0. And if that's the case, the system is uncoupled, meaning that the behavior of node 1 won't be affected by node 2. But most of the time we want something coupled in some ways, and most of the time that they are. All right, so we're going to do this example in the next